Okay, so the next one, the following recurrence relation can generate a sequence of numbers. The number 13 appears in the sequence. This one was pretty easy, isn't it? Which is, would it be? T1 would equal the one before plus 3. Isn't that 13? So T1, 13 occurs at T1. Do we all get that? Yeah, now this one was done pretty poorly in 2022. So let's just make sure if you just do it exactly the same, you'll be fine. So a sequence of numbers is generated and it's shown. What's the value of R2? So if I look at R1 would be 2 minus R0, which would equal 2 minus 2, which equals 0. R2 would be 2 minus R1, which we said was 0. So it's 2 minus 0, which is 2. So D is the answer. So now we're going to look at modeling linear growth and decay. So when we have, we're going to be talking about financial things, so money. So when we talk about linear growth, so we're talking about, so our investments are growing, getting things like the money is getting bigger. It can also be your loan is getting bigger, so maybe the amount. So linear, which actually means a straight line. So if we have when we say modeling, it means a situation. So when we have a financial situation that is linear growth, what we see is, we'll see if we graphed it, we'd see the value over time, so how many, periods of time, we'll see the value go up in a straight line. And that is because the same amount is being added. So that situation at the start with what was his name, Johnny or whatever, where he was adding 250 all the time. So because it's the same amount getting added, that's linear and it will be a straight line. So that, if you look at here, is a recurrence relation of that. That's like a basic formula where you can see this D equals the same amount that's getting added every time. That's just symbolizing that. So in that Johnny application, the D was 250. Okay, so when throughout the notes, you will see the letters indicating, and it just indicates a value or a number. If it's highlighted, it means that you need to change it for your scenario. Does that make sense? So if I was writing out the Johnny thing, I'd look at this and I'd go, all right, it's a simple interest. We'll learn about that. And then you go, all right, D's highlighted, so I need to, somehow I've been told that. And so I'll pop that in when I'm writing it out. Okay, so if that's, and here's an example. Simple interest is an example of linear growth. When you have simple interest, it's when you're getting the same amount added into your investment. So say you had $1,000. If you're getting $10 added, just $10 every week, that's simple interest because it's not the same amount is added every week. Okay, then we will be looking at another one. We'll look at linear decay. So linear decay is when it's reducing. So things that decay are often like, say, value of items or things like that. So, some things devalue, say computers, mobile phones, they devalue over periods of time. So that is a decay. But when we have linear decay, it's the same amount. So that D is equaling the same amount that's getting taken away. Okay, so, and you can see the formula, the recurrence relation has a minus there. So the same amount's getting taken away. Now, examples of this are flat rate depreciation or unit cost. So flat rate is when we say, right, you've got an item that's $1,000, it's going to decrease by 10% of that original cost every time. So 10% of $1,000 is 100. So every time you're taking away 100, that's an example of flat rate. Unit cost is, say I had a photocopy machine that's worth $500. Every time I make a photocopy, it reduces its value by 2 cents. So see how it's going down every time it's used, it goes down, but it's going down by the same amount. So like every time it's used, so it's another flat rate. So we'll go more into it in next chapters, but we're just getting warmed up to it. Okay, so so there we go. So D is the common difference. So if you want to write, you might just want to write the same amount, so that you understand what that means. So the common difference, so that it's always the same amount that's getting done. So when we've been looking at recursion, so we know how we can get the next term using the one before. But say like simple interest, say I'm getting it daily. I don't want to know after 300 days. I don't want to have to keep on going. So what we do is we create an nth rule formula, and that allows us to get the value at any time. So you'll see on your summary sheets at the back, I call this the nth rule, and it's so you can get the value. So if you want to write, get value at any time. Okay, so it's a rule, I should say rule, to get value at any time. Okay, so let's have a look. If we have here let's highlight this. Okay, so here here's for linear growth, and you can see they've written that this is, let's just write next to that so you know. This is the basic recurrence relation for growth, for linear growth. Now, if I want to get the nth term, so here, this is how you create, this is the nth term rule. So this is how I could write out if I wanted a rule. So this is the nth rule for linear. This is growth too, be careful. So you can see the growth is the plussing. So you can see there's a plus in there. Okay, so, and then obviously if you look at the one underneath, we've got here, this is the rule for linear decay, the recurrence relation. So this is a recurrence relation, a basic formula, or I should say maybe, formula for recurrence relation for linear decay. And then here underneath is how we get the nth term. If we want to write an nth term, this is nth rule for linear decay. So let's just go. I believe, so decay is when it's minusing. So I think I've popped in the first question of your chapter. So I'll do it with you to practice. So they want me to write down a rule for AN for each of the following recurrence relations. So I can see that this is a recurrence relation because it's got an AO and an AN plus 1 rule. So what they want me to do is they want me to write the nth rule. So they want me to find a rule that I could find AN and for these relations, and then they want me to actually calculate A20, which is the value of A20. So let's have a look. So if I was doing this first one, so you know that AN. So this is the first one. If I look, this is a growth. So when you write the nth rule, you have to write here, you write VN or AN, and then you do plus, and if you look, you have to do the D. Now, what the D is what's being added on every time. So in this scenario, in A, what's getting added on every time? 2. So we might write, so I'm going to write 2 times N. So just up here, see how they write underneath? They write it N times D. Maybe you can write it around D times N. The reason I do that, because that's how we should really, normally we put the number first. So maybe just underneath them, write that. It's AO. Sorry, beg your pardon. So if we look at that, what's AO in this case? 4. So we should actually write 4 there. So 4 plus 2 times N. So then that's it. And then they want me to get A20. So A20 would be 4 plus, and because N is 20 in that scenario, so that's what we do. And then this one ends up being 44. So then if we look at B, I'm going to convert B. Now B is an example of decay. So they want me to write the nth rule. So you put your VO, which was 10, and then you do minus because it's decay. Now it'll be the D, which is 3 times N. So there's the rule. And if I was finding A20 in this case, it'd be 10 minus 3 times 20, which equals negative 40. If I look at the next one, C, we've got AN. Okay, it's growth. So the first VO is 5. Then we plus 8 times N. 8, if I had to find A20, it would be 5 plus 8 times 20, which is 165. Okay, I'll just pause it and let you guys do the last one. Just to fix up that one, sorry. This one up here was negative 50. Okay, let's do this last one. So AO was 300 in the last case, and it's a linear decay. So it'd be negative 18 times N. If I wanted to find A20, it'd be 300 minus 18 times 20, which equals negative 60.